Okay, so this is the theory of convolutional neural networks. So to recap neural networks, what we have is some vector input, x, which we're going to transform linearly by doing matrix multiplication and then adding some bias to get some features from that input. And we'll apply these linear transformations and activation functions, which is just some nonlinear function, repeatedly to pass our input through the layers until we get some output, y hat, which is our prediction of the label y. And so this will be our function, which takes in x and gives us y hat. But if we want to process an image with a neural network, then what we have to do is some pre-processing where we flatten this image, where we'll just take the rows and stack them on top of each other as such. And when we do that, we're losing the spatial information. So we're losing the features that the fact that these two pixels together might show in the input. So what convolutional neural networks do is have different types of layers, convolutional layers rather than linear layers, which maintain the spatial relationships between features in the inputs and features in subsequent hidden layers. And so now we don't need pre-processing, and the non-vector data can be passed in directly, matrix directly in, and the whole thing is our function f of x. Applications of convolutional neural networks include obviously classification, being able to process images with these spatial features, detection, where we're outputting the center x and y position and the width and height of different bounding boxes to place around different objects that are of interest to us. Segmentation, where we are classifying each pixel, or predicting the probability of each pixel belonging to a certain class, and then you can visualize that by color coding the image in terms of pixel by pixel based on which class each pixel was most likely to belong to. We can also combine them with other models like recurrent neural networks for image captioning. We can pass certain images to we can pass images forward through a model and extract features which represent their content, and we can pass other images through a model and extract features from a network which represent their style, and then by trying to generate a new image which minimizes the style difference between the style image and the content difference between the content image, we can generate these new images which have the style of a style image applied to the content of the content image. And convolutional neural networks are heavily used in doing complex things like playing games. So here, DeepMind's Atari, AlphaGo, AlphaZero, and AlphaStar. All of these, all of the agents which are used here use convolutional neural networks to process the input. So to mention images as data, what that actually looks like is not just a matrix of width and height. If it's got color, then it's probably going to be an RGB image. What that means is that this image also has a depth where the different layers represent the different channels, the intensities of pixels of a certain color. So the first layer in this, the first channel in this image represents the intensity of red at any given spatial location, and then the same for blue and the same for green. So if we were to split an RGB image into its constituent channels, then what we'd see is a representation of the intensity of red, green, and blue as separate 2D images, in which case these would all have a depth of 1. But what we see is a combination of those three intensities at any given location. So linear layers work by taking different rows of weights and then multiplying each element-wise with elements in the input. And so we will learn these weights such that the dot product between each of these rows, each row in the weight and the input activate, which means they give a high number when a certain feature is present. So the dot product between a row and the input will give a single value in the output layer, which should be representative of how present is that feature which this set of weights was looking for. And so to process an image here, or any 2D or higher dimensional data, then we'd have to flatten the image. So unroll it into a vector. And yeah, so each row of weights linearly weight each input feature to form a single output feature. Convolutional layers, on the other hand, process images directly, and the way they do that is, instead of having weights where weights which have an element for each weights which contain weights for each feature in the input, these weights in the convolutional layer are actually filters. So what they are is basically similarly to weights in linear layers, patterns that we're looking for, but now we're going to apply them all over the image. So this doesn't mean like linear layer we're going to apply them to every point of the image at once. It means we're going to apply them to a small region of the image at one time, and then extract a feature from that, and then use the same filter in a different location so that we're looking for the same thing over the whole image. So you see what I mean in a second. So what we're going to get from that is a stack of now not 1D representations of features, but 2D representations of features, where each different region in these activation maps will have a high activation if the feature which the corresponding filter is looking for is present in that position. So to gradually get more concrete, what does this mean? So we'll take this weight, which I said has height and width of k and a depth of c, so depth all the way through the input activation map, which it's looking at. We're going to take that weight and just drop it over the top left. We're going to start with the top left region of the image. Then what we're going to do is we're going to take an element-wise product of the filter and the features in the image in that position, and then sum them up just to form a linear combination of the weights and the features, just like in a linear layer. And then we're going to take that linear combination and put it here. So what this number represents is how present the feature which this filter was trained to look for is in this region of the image. Then what we're going to do is we're going to look for the same pattern represented by these weights in another region of the image. So we're going to take that filter away and then reapply it, just shift it along slightly. And then again, we'll take a dot product of the filter weights and the features in that region of the image, and then we'll place that in our activation map here. Do the same again, take the filter away, put it back, just shift it along slightly, and then the product represents the activation of the feature which this filter is looking for in this position. And weights will always cover the full depth, that is all channels of the input activation map. So what they're going to do is they're going to form some combination of different features in different spatial locations and also in different activation maps. So where each different activation map might represent the presence of some other particular feature which those filters were looking for. So in the case of detection, so maybe one of these filters, this one is looking for faces, whatever, and so when there's a high number in any region of this red activation map, that means there's likely to be a face here. I can see features which resemble a face, and this green one might be something different, like cars or whatever. So we'll be able to see how present the feature is by each of these numbers, but we'll also be able to see where it's present in the image. So convolution looks like this, where we're sliding some filter over the whole image, and every time we do a new location, every time we convolve over a new location, we get one single element which contributes to our feature map for the next layer. So for example, like this, if we've got a 5x5x3 filter here, well, that's going to be 25 features in each channel, 3 channels, 75 features, 75 weights in each filter. And then what we'll do is we'll take those the features of the input in the corresponding positions, obviously similarly 75 of them. Then we'll take a dot product between those two things, just multiply them together. And then what the weights are is a pattern which this filter is looking for. So yeah, note that we didn't have to keep them in their tensor shape. We can just unroll them into vectors and then do this product. And what this product is looking for is the match of a template which the filter represents. So the filter is learnt to represent some useful feature, and then when the features of the image are resemblant of that feature, then the product of those things will increase, and so this will be a larger number. And then we'll add a bias as well, just as an offset. And so that product will end up here in this activation map. This red one corresponding to this red filter at this blue position. And so each convolution produces a single pixel in the activation map, which represents how much the filter was matched in that region. And so we can make different design choices within convolutional layers, and we'll talk about those in the next slide. But those are the stride, that is the step size of moving the filter around, the kernel size, which is the size of the filter, and padding, which is basically what we do to the edges of the image, which we'll talk about in a sec. So convolutional layers are powerful because each layer is going to require much less parameters than compared to a standard neural network, for example. So if we were to map between these two layers with a convolutional layer, let's say we have filters of this size, and we have 4 of them, as I drew in the previous slide. So we've got 5 by 5 by 3. That's 75 parameters per filter. We've got 4 filters. Then we have then we have 300, and then we've got a bias for each of those. So 304 weights in these layers. If we were going to have a linear layer, on the other hand, then we'd have to have weights between every feature in this input and every feature in this output. So the number there would be 32 by 32 by 3 by, this would end up as 28 by 28 by 1, and that's going to be way larger than the number of weights we're going to need for convolutional layers. And yeah, obviously, as I've said before as well, we can build features now that interact spatially, and so that's like a big part of what can make up meaningful representations in an input. So the stride, I'm just talking about these design choices. The stride is the step size. So in this case, I've drawn a stride of 2. So now we're not just moving the center of the filter 1 along every time, we're moving it by 2. So what this does is helps decrease the size of our activation maps. That's the first thing it does. So if we were to move this purple filter just along by 1, then we'd be able to fit in 5 convolutions along this image. So the output size of the output activation map from this layer, from this convolution operation over this whole layer would be 5 by 5. With a stride of 2, the output's going to be size 3 by 3. And that means that we're going to have to store less values which make up that activation map, so the memory complexity is going to be lower, and also we're only going to have to process 9 convolutions rather than 25, so that's 3 by 3 and compared to 5 by 5. And that's going to make our model faster during the forward pass, because we don't have to convolve over every location, just every other location, essentially. Padding is, like I said, what we do to the edges. In this case, what we've done is 0 pad the edges. And so without padding, the edges of each input to a convolutional layer are sampled from less. So if we didn't have this padding, as in this top example here, then this top left feature would only appear in one, it would only contribute to the output of one convolution, which is where this purple filter is. As soon as we move this purple filter along to here, then no longer is this, this feature isn't going to be present in any of the other convolutions. When we add padding, however, it's going to appear in as many of the convolution operations as any other filter in the image, as it should, right? Because there's no reason why the important parts of an image might not be on the edge, right? So yeah, another really important thing is that without padding, activation maps decrease in size through the convolutional layers. So as I said in this example, if we had a stride of 1, then the output would be 5 by 5, and the input is 7 by 7. If we did the same thing on that 5 by 5, then the next output would be size 3 by 3. And so every time we're doing convolution, the size of each layer is decreasing. And what that means is that once we get to 3 by 3, if we're using a 3 by 3 kernel, then we can only fit one convolution in there. So we end up with just a single value. But the problem with that is that we basically want, that puts a limit on the depth of the model, and we know that neural networks through subsequent layers, they build features upon features. If we can only get to a certain depth of features, then we might not be able to have enough. We might not be able to have complex enough of a hierarchical representation, building on more and more complex features to represent the input-output mapping that we want to. So yeah, without padding, there can be a limit on the depth of the model, and that limits the capacity. So for this operation, what are the stride, padding, and kernel size? So let's say that this is just an image, and we haven't padded the edges, so padding 0. Stride, we're moving this filter along by 1 step every time. So the center starts just here, moves to there, 1 step every time. So stride of 1. And the kernel size, here we're looking for 3 by 3 patterns. So the kernel size is 3 by 3, obviously by the full channel depth, which is 1. So these examples, we just want to think about what's going to be the size of the output activation map using these convolution operations, where I've said S is the stride, N is the width and the height, they're square examples in this case, and K is the kernel size. So if we're convolving over this 7 by 7 input, how big is the output going to be, right? With a stride of size 2. So we'll be able to fit one convolution there, one here, one there, so that's 3 wide, and then the same down. So the output is going to be 3 by 3. And then in this case, so we have a kernel size of 3. We're taking steps of 3, so 1, 2, 3, end up there with a center. Do another convolution there, and then again another convolution there. So we can get 3 across, and then it'll be the same down because it's square. So the output again for each of these actually is 3 by 3. But there is a short equation to compute that, and that looks like this. So we'll take the width or height, or n if it's the same, subtract the kernel size, divide by the stride, and then add 1, and then that'll be the dimensionality of the output shape. And so obviously you can see how we could play around with these design choices of the convolution to actually not even decrease the size of an activation map, which means we can have we can have depth not limited by convolutions, but because the size is decreasing every time we do them, and we can do that by adding padding. So yeah, going to end up with both 3 by 3 through that. So putting these convolutional layers to use, we can build a convolutional neural network. And so what that consists of is taking some input, convolving over it to form another tensor output for that layer, then applying an activation function to every value in the output, and then repeatedly doing the same thing again. So applying convolution, activate, convolution, activate, convolution, activate, until we've extracted what we believe or have tested that can be sufficiently complex features from our model. So just get it back up. Yeah, so we'll apply those convolutions to extract increasingly complex features whilst retaining the 2D, the spatial relationship between the features. And then when we get to here, in this implementation of the model, we actually do unroll it into a vector. So we assume in this point that each of the features is sufficiently complex enough and sufficiently, low resolution enough that we can just unroll it into one long vector and then perform some standard linear layers with a standard neural network at the end. In this case, we're doing classification of 1,000 different classes. And so what we want to output on the end here is a probability for each class. So yeah, each layer builds on the features from the previous layer, so the network learns hierarchically more complex features. So in the beginning layers, what we're only going to be noticing low-level features, things like edges, and then building on those edges, we can make things like certain shapes, and then building on those shapes, we can actually start to build up abstract representations of more complex objects. And then after we've extracted those complex features, we can use linear layers to classify them. Right, now we're doing implementation.